Okay, I guess we can get started. Hello everyone, welcome. Today I'm very happy to introduce our speaker, Jiahui Liu. She is currently a postdoc at MIT, and earlier this year she finished her PhD from UT Austin with Scott Harrison. And her research is kind of in the intersection of quantum computing and cryptography. And today she's going to tell us about quantum money. Welcome, Jiahui.
Hi everyone, I'm Jiahui. Today I'm going to present work on quantum money. The title is a bit long. It says how not to build quantum money from lattices. And the second part is kind of independent from the first part. We were going to talk about how to build quantum money from something we call workable invariants. This is joint work with Hart, Montgomery, and Mark Gentry. Okay, before going into what quantum money means, I think probably something more well-known about quantum is that quantum computers have the power to break most of the widely used modern cryptography tools, such as factoring and discrete log. And if you guys have some touch with public key cryptography, basically most of the things that are widely in use right now can be broken by a full power quantum computer using something called Shor's algorithm. So on the other hand, I guess it's probably less well known to the classical community. So for researchers not in quantum, is that actually quantum computers do not just bring in devastating power to cryptography. It's also bringing things that's positive and constructive. So using quantum information, we can actually build new cryptographic tools which are in some sense impossible if we only work with classical information and classical computers. So here are some examples of famous cryptography protocols based on quantum information. The first one is called quantum key distribution. This is a protocol where you don't even need full power quantum computer, but you just need robust quantum communication channels and some sort of ways to store quantum states, to store quantum memories for a short while. And this allows you to do key exchange protocol where Alice and Bob can send messages to each other and got to share some secret key they can use. And this is something you can only do with these public key. It's in the zone of public key cryptography, and it's not information theoretic. It's not something you can do without assumptions in the classical world, but this is something you can do information theoretically if you work with, if you allow Alice and Bob to send quantum information to each other. And there's quantum money, which I will soon talk about. And there's also something called quantum position verification. I don't think I have time to go into, but classically, position verification is a protocol where you want two provers to bound the distance of, two verifiers to verify the location of a certain prover using the bounding of distance by sending messages to that prover, and the prover must reply an answer to both of the verifiers in time. And because the time is bounded by the speed of light, that it can, like, no information can travel faster than that. So if the prover is standing at somewhere else, it will be found out. But this is actually also impossible classically when you consider the situation where there are multiple malicious provers trying to impersonate themselves as one prover at a certain location. Unless you use hardware assumptions, you cannot do that classically. But quantumly, you can, if you allow the verifiers to send quantum messages to the prover, you would also be able to obtain secure protocols. And there are still a lot of others, but I will not go into what these protocols are. The interesting thing about all these quantum protocols is that they have something in common. They all somehow or somewhat rely on a certain quantum mechanical principle called no cloning principle. So what is the no cloning principle? It says that quantum states cannot be copied in general. Basically, it says when you are given, I just give you a quantum state. I don't tell you how it's prepared. I don't tell you what's the description. So if you are familiar with some basic quantum information stuff, you probably know that quantum, for example, a qubit, it's a superposition of classical bits, right? So, for example, if I tell you, oh, this is an equal superposition of bit 0 and bit 1, of course, it will be easy for you to copy because you know the description of the state and it can be prepared. You can just prepare as many copies as you want. But if I just give you some arbitrary quantum state, it will be observed mathematically that there is no general procedure to turn this unknown state into 2 copies because this procedure is nonlinear and it does not preserve norm. The norm L2 norm of the quantum states when you view them as vectors. So this is a very simple information theoretic statement. We want to apply this principle to cryptographic protocols. So one thing is, okay, now we have something that cannot be copied. So we want to use such a principle to go against behaviors such as forging money or forging signatures, for example. So actually back in, I guess, 50 years ago, someone called Wisner, he already had such a pioneering idea to use this principle to go against piracy and forgeability. And he put forward the notion of quantum money. And this idea was basically the first real application of quantum information, and which actually inspired many of the protocols I mentioned just now. So what is quantum money? In a quantum money scheme, a bank can prepare a money state and issue it to a user. And this money state is a quantum state that encodes a money value and a serial number. And a user with a valid money state, which it gets from the bank, should be able to spend this money whenever it goes to the bank and say, okay, I have this money state in my hand, just verify it for me. It says $1. Okay, the bank should be able to verify and says, yes, it is a valid money state. You should be able to use it in transactions. However, suppose a malicious user, after receiving one copy of the money state from the bank, it tries to just try all kinds of means to make 2 copies so that he can double spend this money. He should not be able to do so. So this is the security requirement. The previous one is the correctness requirement, and this one is the security requirement, is that no user should be able to produce 2 copies, so that both of them will pass the verification. And note that I will go back here later, is that when the bank generates this money state, it must first sample, usually it's a classical string, a classical secret key to generate this money state, which I put in this cat bra $. And when the user goes to the bank and says, okay, verify my money state, the bank also have to run this verification algorithm, which has to use this secret key to verify the money state. And this is something we call secret key quantum money. Basically, that means only the bank using the secret key should be able to generate money states. And also, only using the secret key, you should be able to verify the money state. And it's not like everyone else in the world can verify the money state. Okay, so let's take a look on the talk outline. I will first briefly talk about why we care about quantum money and the history on quantum money. Then I will present the results in this work. The first part of the result is an attack on a public key quantum money scheme that was proposed last summer, which was based on these famous post-quantum assumptions called lattices. Then I will present, on the other hand, so the first one is attack on a proposal, and for the second half of the paper, we will present our own proposal to build quantum money. And I will briefly talk about how we could possibly instantiate our proposal using concrete assumptions, because our proposal is using assumptions that are not quite falsifiable. Okay. So why does quantum money matter? So as a quantum cryptography researcher, I would say it has been and probably will be one of the central topics in quantum cryptography, because the thing is that the quantum money was basically the first quantum primitive that inspired all the later works. And despite that, it had a construction for secret key quantum money back in 50 years ago. There is still a lot of problems unsolved. One thing I will soon mention is this main topic we will talk about today, which is public key quantum money, that everyone in the world can verify your money state, so that you don't have to go to the bank to do your transaction. The bank, there is some decentralization involved in there. And we would even want to decentralize such a scheme even more, in that even the bank or like someone we call mint, like not necessarily the bank or like Federal Reserve, they can issue money by themselves. And but the thing is that even the mint who can generate the money state should not be able to generate two copies that have the same serial number. And such a protocol can allow you to do things like a blockchain without chain. And the second thing why it's important is that it's classically impossible. As I mentioned, classical information can always be copied, right? So even if you just give out a classical message, no matter, you can sign it, you can obfuscate it, but the information itself is still classical. If someone wants to copy this information, he can copy the entire signed message or the entire obfuscated message, the entire encrypted message, and that can be of some use, even if it's not decoded. So the thing about quantum is that there is simply no way to just duplicate the message itself. And also in quantum cryptography, quantum money sort of acts as like a central node that connects to a lot of these other quantum primitives, which are have many applications. For example, like some of these quantum things that they need like more background, but I will just talk about one thing. For example, something we call copy protection of softwares, where you want to encode a classical functionality. For example, it's a video game into a quantum state, so that when someone buys your game, you give this state. So he has this state, he can run the software, he can play the game, but he's not able to generate two copies so that both of these copies can help someone play the game. So this is an extension of quantum money, where you can do anti-piracy, unforgeability for something for more complicated information. It's not just a piece of information that says this is a piece of money with $10 value. It's like more complicated information, and all these things. If we want to do them from better assumptions, we have to build quantum money from better assumptions first. Okay, so let's go back. So as I mentioned, there are actually two types of quantum money. The first one is the easier task. We call it private key quantum money. In the private key quantum money scheme, the bank has a secret key. It uses the secret key to generate a money state. And when someone wants to verify a money state, it has to get in hold of the secret key as well. So usually in our case, it is the bank who is the only guy with the secret key. So everyone who wants to do some transaction must go to the bank and ask him to verify the money state. And this can be built, as I mentioned already, 50 years ago, there was a secure construction. It uses something called conjugate coding. Basically, the scheme samples two random strings, n-bit random strings, and it encodes each bit in the first string using the basis specified by the second string. So if you, go ahead.
Why is private key quantum money easier?
Oh, okay. So yeah, because by easier I mean it compared to later goal, I will mention the public key quantum money, where everyone can verify the money state. So the intuition why this is easier is that with the secret key, right? So there is very little information leaked about the money state, right? Everything is in the hands of the bank. When you hold a fake money state and you go to the bank, says verify this for me, the bank will say, okay, it's fake, and the bank can then say, okay, I need to destroy this fake money for you, and you can't do anything anymore. The thing is, with public key quantum money, you have to publish some information that's relevant about the quantum state, right? About the quantum state that encodes the money. Publish it out there, and everyone can access this information. But on the so this makes the thing so much harder when you want to prevent people from duplicating it, because there is actually non-trivial amount of information out there everyone can see, and they may be able to learn the money state just from that public key. You want to prevent that from happening. So this is intuition why it's hard. Okay, so going back to secret key, private key quantum money or secret key quantum money. Okay, this scheme it encodes the first string bit by bit. So for example, if you are familiar with some quantum basics, there is like two bases which anti-commute. If you know that, for example, Heisenberg's uncertainty principle is basically if you get to know the information of one basis, you will completely lose the information of the other. So you encode your string in those 2 bases randomly, and basically this quantum state in the views of a user or say a malicious adversary, even unbounded, it will be something like we call completely or maximally mixed state, and that you can say it's comparable to saying uniformly random, like classically. So there's no information about the state, no information about the secret strings or the secret basis. So only the person who knows the basis theta should be able to verify this entire state, checking whether it's encoding the correct bit under each basis. And also there is something called quantum money from pseudo-random states. I will not go into, but in fact there is a bunch of ways of building private key quantum money. Basically, to build a private key quantum money, you just have to sample a classical random string and prepare a state where the preparation is efficient, because you want your money issuing procedure to be efficient. And if you can show that this state is unclonable, then you are good. So there may be like a bunch of ways out there to do private key quantum money. Yeah, but as I mentioned, there's a huge drawback, is that the entire protocol of using private key quantum money is highly centralized. Everything is done by the bank. The issuing the money is done by the bank. Verification is done by the bank. If Alice and Bob want to do a transaction, they have to go to the bank, and that's very bad. So what do we really care about nowadays is something called public key quantum money. And as I mentioned, this is the harder task because you have to publish some non-trivial information about the money state out there where everyone can see, because everyone needs that information to verify the money state. So when the bank generates the money states, it together generates it with a public key. And of course, as I mentioned, the money state should also come with some serial number to specify the uniqueness of the state. And the adversary's goal is, of course, to generate 2 money states that correspond to the same serial number. And when someone with a public key, basically it's everyone can come and verify if if both of the states generated by the adversary can pass this verification using a public key, then the adversary wins. And we do not want this to happen. And now we go into this world of public key quantum money. I will briefly mention that we can no longer stay information theoretic. So the previous private key quantum money scheme is actually information theoretic. As I mentioned, even unbounded adversary, in the eyes of the unbounded adversary, this quantum state is completely random. However, in the world of public key quantum money, there's no hope of doing it information theoretically without computational assumptions, because one easy observation is that if the adversary is unbounded and there's the public key, the adversary can simply enumerate prepare all possible quantum states and try them one by one, plug into the verification algorithm using the public key, right? Because it's public, the adversary can see it as well, and check, okay, is this current state the correct bounding state? And he can go on forever until he finds the correct state. So right now, the adversary must be bounded. And as I mentioned, there's even one more useful primitive that is even the bank or the mint cannot generate two copies of the money state. So quantum money, in quantum money, there's a generation algorithm that generates a money state and give it to the adversary. The adversary, given this specific copy of money state, the adversary cannot produce two copies. They're both positive information. And then there's something called quantum lightning, where there's something we call common reference strings. You can view it as some random string that's published out there in the air where everyone can see. That can be used to generate money states. So basically, the adversary is able to generate the money state on its own. However, it's not able to generate two money states that correspond to the same serial number. So to understand this more intuitively, I would say I would put a classical analog of these two security notions here. The classical analog of quantum money is a second pre-image resistance. That says I give you something, a very specific challenge, and I ask you to find two collisions correspond to this specific challenge. Okay, so you are given like a fixed challenge at the very beginning. And on the other hand, quantum lightning is like collision resistance. He said, I don't fix any challenge for you. You just try to find collisions however you want. As long as they count as a collision, you win.
I have a question. Why do you need a serial number here? I don't quite understand.
Oh, so the thing is, if you don't have a serial number, usually the serial number is usually signed by the bank. It's like if you don't have this kind of classic information, everyone can generate a money state, right? Because for example, we know that the procedure of generating money state itself is the algorithm itself is public, right? So usually about what's important about cryptography protocols is that you can't assume the protocol or the algorithm is private. They're always public. The private thing is about the randomness you use will generate something. And when the bank generates the money state, they also generate it with a serial number, and usually the bank has to sign the serial number and the public key and says, okay, this is a money state generated by the bank. And
so is it only necessary when you move to the public key situation? Because in the secret key construction, it seems like you don't necessarily.
Right. I think so. Let me see. In the secret key setting, yes, I think even if there is some serial number, it's only in the bank's memory. It's like used by the bank to keep track of, okay, like the serial number corresponds to like a secret key for this state I issued. So when someone comes, I think it still comes with a serial number, but it's not as like important as in the public key case. So you can think of in the secret key case, you can think of the bank's memory as like it keeps a large table of all the money state has generated, and simply the serial number is simply an index that specifies, okay, for this one I need to use this secret key because every time it samples fresh random secret keys. So when someone comes, it checks, it just look up the table to check for secret keys. Yes, and in the public key case, the serial number specifies like the uniqueness of this state, and it specifies, okay, this is one new money node is generated by the bank, or in the Lightning case is generated. Yeah, I think in the Lightning case it's particularly important because everyone, in some sense, everyone is able to generate money states in this setting, and probably they will they will try to use some consensus protocol to maintain the whole economy. But the thing is, if you don't have the serial number, you do not know like this is like a unique money state or something. Okay, so as we can see, quantum Lightning is an even stronger primitive because right now I basically allow everyone to generate money state. I'm simply saying no one is able to generate two money states that correspond to the same serial number. Just as Pei had asked, there may be some confusions like on why we need the serial number. Basically, we can view the money state and its public key and the serial number as binded together. When you receive a money state, when you want to verify it, you first verify that whether this public key and this serial number is signed by a particularly trusted party, and also you use this specific public key to verify this specific money state. So it's not like one public key out there where everyone can verify like all possible money states. So next, let's look at a history of quantum money. And it's sort of a history of struggles because a lot of these proposed schemes are actually broken. So I have all these ones with these orange checks here. They are the ones that remain unbroken. So basically, they either use very strong oracles. So by oracle, I mean it's a circuit that's published out there, but you can only use it as a black box where you cannot see the internal structure of the circuit. So it's kind of a powerful tool. Basically, you are saying that I just put out some in many settings, it's a very complicated program out there as a code, but everyone who can use the code, to them, it's no different from just running an oracle, just using a black box, which it only sees the input and output behavior. So, and one slightly better assumption is, it's actually much better, but not good enough, is using quantum secure I/O. So I/O is something called indistinguishability of falsification, where it's a concrete cryptographic primitive that you can scramble the code of a circuit so that it looks sort of unreadable and you cannot tell what the circuit is doing. So it's kind of similar to what you want with oracles, but the assumption itself is a lot weaker, and it can be constructed from concrete mathematical cryptography assumptions. And for quantum Lightning, so as I mentioned, Lightning is an even stronger goal. So it's like even more far-fetched. So there is like a lot of candidates. I think these ones in orange, they are the candidate for quantum Lightning, and some of them are broken. The ones with a cross after it are broken, and the other ones I put a question mark. Basically, it says, okay, we do not know. And in this work, our major contribution is that we first rule out a class of quantum money. So we rule out a particular way to build quantum money from lattices. And we also put forward another way of building quantum money. We give a framework to build quantum money. And this framework does not rely on specific mathematical assumptions, but it says if some mathematical structure satisfies certain restrictions we need in our money scheme, then you should be able to use it. And if you believe those hard problems are existing in those mathematical structures you want to use, then it makes up a quantum money scheme. So I will go into the first part of technical contents. I think we only have half an hour left, so I will try to be brief on high level. So I guess probably if you for people outside cryptography community, one question is why is attacking a particular kind of quantum money protocol important? Like why is why is it even worse working on attack? Because the first thing is, even though this protocol is quite new, it's not something we're attacking something quite established. But the problem of building public key quantum money from lattices has remained an important problem in the quantum community. Because as I mentioned, everyone knows that quantum computer breaks a lot of classical mathematical assumptions that you used to build cryptography. However, there are like few assumptions. One of them is the class of assumptions called lattice-based assumptions. They remain, at least to the best of my knowledge, at least to now, that they remain intact. They are not attackable by efficient quantum algorithms. So, of course, when we build quantum money, when we want to use mathematical assumptions, since we're already dealing with quantum adversaries, we have to use these quantum immune assumptions, such as lattices. There are a lot of other candidates out there for quantum-resistant assumptions, but lattices are certainly the best, the most well-studied and the most well-known assumption. But it remains unknown, like from such useful and widely applicable assumption, like why can we not build quantum money? The thing is, people are interested. This is like the most natural and assumption that you want to use to build a quantum money scheme. And the assumptions we use in here is one called short integer solutions. So basically, you are given a system of linear equations, and you want to find a vector in the kernel of this matrix A, and this is actually underdetermined. So there are actually a bunch of solutions for this vector, and it's usually easy to find if I don't restrict anything else. But the thing is, I restrict the norm of this vector to be short, to be bounded by a certain parameter. And when you restrict that, the problem gets hard. And then there's this problem called learning with arrows, and it's also saying, okay, I will give you this random matrix, and also a secret. I will also sample a secret vector S, and I ask you to solve a system of linear equations. And in fact, in this setting, the S is uniquely determined by the equations as I will give you. However, I will mask this linear system by some small Gaussian distributed arrow so that it will be hard for you to find S after I mask this system. And in fact, it will even be even if I just ask you to distinguish the system from sampling a uniform random vector from the entire field will be still hard. And so I will go into this public key quantum money proposal, which is based on the short integer solutions problem. So in this scheme, some trusted authority or probably through some MPC protocol, we can sample a public parameter, that is this uniform random matrix A, where you have dimensions over ZQ, where you have dimension N over M much larger, but I will not go into those details because those are simply things required by the structure of the assumption. Okay, and how do you generate a money state? To generate a money state, you first prepare a Gaussian weighted superposition of short vectors. This is something, I think things may get technical here, but I will try to give classical analog for everything I say. So how to prepare this state is in fact very similar to classical rejection sampling. Is that you want to sample vectors according to the certain distribution. If you don't get it, you just discard it. Okay, and when you prepare this superposition, now you apply this public parameter A on your quantum state, and you measure the output. So what you will get at the end is that you will get a state that satisfies two constraints. The first constraint is that they are short, because I prepare everything in the quantum state to be short at the very beginning. So they are short according to this Gaussian distribution, which means the probability that their norm is larger than a certain amount is very small. So, and the second constraint is that since you have applied this matrix A and measured it, and you have obtained a random value U according to your measurement, and everything in this quantum state will also satisfy the constraint that when you apply A on these vectors Y, you will get the value U which you measured, and of course everything, all the computation is over mod Q. So why do people think this leads to secure quantum money? Let's look at what happens if the adversary is able to make 2 copies of this money, and I will claim that it would break the previous assumption called short integer solutions that I put forward. So okay, suppose you can measure, right? You get one copy of the money state, and of course you can always just do a simple measurement to the quantum state. And if you do that, it collapses to one of the strings in the superposition, which is some short vector y that satisfy AY equals U. And suppose you have 2 copies of the state. Since it's a superposition of many such y's, if you have 2 copies of the state, you measure the first state, you would get something of short vector y1, and you measure the second state with very high probability, you will get something else. You will get y2, but y2 will also satisfy this constraint because the entire money state, it consists of superpositions of different vectors which all satisfy these 2 constraints. That they are short and they satisfy AY equals U. And you see that since when you apply A, they will evaluate to the same U. If you simply subtract these 2 vectors, their difference, y1 minus y2, the vector would be in the kernel of A. So that would satisfy A times y1 minus y2 would give you 0. So this is giving you a short integer solutions, because in short integer solutions, we ask for a short vector that's in the kernel of A. Now we have a short vector in the kernel of A. Very easy, just by taking the 2 duplicated money states from the adversary and measure them and subtract. Okay, so this is the intuition why people think this construction leads to a secure money scheme. However, the thing is that I did not mention how you publicly verify. Let me take a sip of water. I did not mention how you can publicly verify such a money state. The thing is, the intuition is that you cannot simply verify the whole superposition by checking the computational basis that if everything maps, after you apply A, everything maps to U. Of course, it does satisfy that, but what if the adversary just measures the state itself and make 2 copies of a classical string Y? It would still satisfy this constraint. So you have to take use of the quantum structure in some sense. The thing is, what you can do in the quantum setting is you apply a quantum operation called quantum Fourier transform, and this allows you to go to another basis. We call it Fourier basis or a Hadamard basis of the quantum state, and you can verify the structures of this state. I cannot go into details for this part because it's kind of technical. The magical thing about this quantum state is that if you apply this quantum Fourier transform, you would actually go to a quantum state which is a superposition of LWE samples. That corresponds to the same matrix A. And suppose you can verify whether the state after the quantum Fourier transform are valid LWE samples, then you are good. Then you should be able to say, okay, this state you give me is exactly what I want. But however, this approach simply doesn't work because you cannot verify whether the state after the QFT is a valid LW state simply by the security of LWE, because the verification procedure itself has to be efficient. And we can basically show something like if there's an efficient procedure that can distinguish a valid LWE state, which is the state under the quantum Fourier transform, from something random, from, for example, a random uniform superposition over all strings of the same size, then you are already able to distinguish LWE, classical LWE samples from uniform random. So that is basically something that violates our this harness assumption here. So this is a very well-known and well-studied assumption. So if you believe this is hard, then there is simply no efficient verification procedure. And to see even more why this this previous proposal doesn't work, is that in fact by the hardness of LWE, you simply cannot tell whether this money state has been measured or not. For example, the adversary can cheat via a very simple strategy, is that after it receives the money state, it measures it, right? Measure it, it gets a classical string Y and make 2 copies of it. And it simply hands in this state to the verification procedure, and the verification procedure cannot tell that this is actually a measured state by the security of LWE. So this is kind of a magical property. Go ahead.
How does the adversary measure that state? Given that is the base public?
Sorry, I did not quite get your question.
The measurement base public, the base in which the adversary can measure the quantum.
Oh yeah, yes. The basis it measures the computational basis. So it's like a public basis. It's like not something arbitrary. It just measures in the computational basis, and you can assume the state itself is when the bank gives it to you, it's encoded in computational basis. There is no trick done by the bank. So the adversary just measures it directly upon receiving the state and make 2 copies of the classical information it obtains. Okay, so this says why the previous reduction does not go through. In our previous roadmap, we say, okay, we are going to get 2 different vectors from the fake money states provided by the adversary. But here the adversary is in fact not producing any new vectors. It's simply producing one vector Y, and give it to you. And we are not having 2 different vectors, so we cannot subtract and get a short integer solution. So there's a bunch of questions left. So for why this, how to fix this previous scheme. So there's still some sort of subtlety in there that there's probably some very narrow regime where you can sample the matrix A, the public parameter A, in some weird way so that you can make decisional LWE problem, which is the problem distinguishing these samples from random. You can make it easy, right? So that makes the verification easy because our verification is sort of just doing distinguishing LWE samples from random. But at the same time, you want your short integer solutions to be hard because this is the harness you want to build your quantum money on. And so there were these attempts by Cashin, Liu, and Shor. So this Shor is in fact the Shor's algorithm guy, and they propose a fix to this scheme. Due to restriction of time, I will not go into their details. The high-level intuition is that they want to sample this A up to some structure that they already give out some vectors in the kernel of A, and these vectors in the kernel of A would help you do the verification under after the quantum Fourier transform. However, they want this whole thing to the money state to still be hard to duplicate because of this a variant problem called K short integer solutions. Is that I give you some short integer solutions, but I ask you to find a linearly independent short solution, different from everything I give to you already. Okay. However, we show that this fix still doesn't work, and this in fact requires a lot of non-trivial work. We will show that the kind of quantum money scheme they they can build from this assumption. They use in fact are still computationally there's still a way to build an efficient fake money state simply by measuring the state and taking use of all these public parameters, these short integer solutions given out. And what you can obtain from such a forging procedure is something computationally indistinguishable by LWE. So it's kind of a different forgery procedure. You have to measure the money state, get some information. You have to take use of things in the public key to make a forgery, which is actually a superposition instead of a classical information. So it's a more involved attack. But the thing is, nevertheless, it's the inherent challenge is still that verifying the quantum money is equivalent to distinguishing. It sort of implies distinguishing LWE samples from random. So. Okay, so the takeaways is that we can rule out a large class of short integer solution-based quantum money scheme by our work. And okay, you guys can ignore the second item. But the most important thing is that we're not saying you cannot build public key quantum money from lattices. We are simply saying there's a particular approach which looks natural and looks promising at first glance, but in fact, when you actually open up the proof, you will say that the verification is simply impossible computationally. Like if you have efficient verification, you can also have efficient attack in substance. If you believe in the hardness of this well-known lattice problem called LWE. However, it still remains wide open. There may be other ways that's completely different from our current approach to build public key quantum money. Okay, so we do not have much time left, so I will just take a very quick walk through our second part. And said, okay, now we say, okay, one approach of building public key quantum money is done. Let's try something else. So all these verification approach, in fact, exist that exist there in these works. They're kind of similar in some sense. That when you verify a quantum state, you verify it first under the computational basis, then you test it under the Hadamard basis for some structure. So what if we do something else? There is actually quantum state can have many different structures other than just having them under the computation and the Hadamard basis. So we would like to propose a structure called walkable invariant. So in a walkable environment, we have some abstract mathematical structure. The first thing is we have a set X and a set Y, where you have a mapping. We call it invariant, so abbreviated as I, that maps the things in set X to the things in set Y. And inside the set X, there are things we call orbits or subsets. You can view them as some sort of equivalence classes or orbit in group theory, but they are not necessary group structures. We just use the term as for intuition. And the thing is, inside each orbit of this set, inside the same orbit, everything after you apply the invariant I will be mapped to the same Y. So you can view this invariant I in some sense as mapping for the orbits, because everything inside the orbit will be mapped to the same Y. There's no difference. And there is some there's some more structure that is a permutation we call sigma. Using permutation, this sigma can be it's in fact a group of permutations where you can operate on these elements in X. I claim that inside each orbit, if you just pick two random elements, there always is a way to permute one element and to go to the other. So there always exists a sequence of sigmas that allow you to apply the sequence of sigmas on element 1 and go to element 2. But they must be inside the same orbit. Okay, so basically inside same orbit, you can always permute them in some sense. You can always go from one element to the other, and there's also inverse to go back. However, there is no way that you can use this permutation to go to another orbit. For example, I apply a sequence of permutation to something in orbit 3. There's no way I can get an element in orbit 2. So it's kind of a closure property. There exists no sigma that permutes one thing to the other in different orbits. And how do I use this to prepare Mani state? Is that I first, so let's say this set X is efficiently sampleable. For example, everything can simply encoded by binary strings of size n. So first I simply sample a uniform superposition over everything in the set. Okay, as I claimed, for example, it's simply a uniform superposition of all n-bit strings. And then I compute this function on these strings, and I measure them to get an outcome y. So since this measurement is completely random, I will get a superposition of all the x that map to the same y. So now the Mani state will be a superposition of all the x, and your serial number will be the outcome of your measurement y. So this y comes completely random from your measurement. And you can imagine that, for example, everything here in the superposition, let's suppose for a simpler structure, so each orbit will be mapped to a different y. For different orbits will be mapped to different y. So some sort of an injective sense in terms of orbit mapping to the set y. If you have that, then this Mani state will simply be a uniform superposition of everything in some certain orbit, where this orbit is specified by the invariant to the set y. And the thing is, okay, how do we verify this Mani state? The verify is that, okay, now we know that a valid Mani state, when I see the serial number y, the serial number y sort of specifies which orbit this state should have. So a valid Mani state should be a uniform superposition over everything in this orbit that's mapped to y. So I simply do a projection onto this orbit corresponding to y. This may not be very intuitive why it's doable. Why it's doable efficiently, because you do not know what this orbit would look like. This is not. It's not something you can efficiently prepare. If you can do that, you can actually do the tag. So I will just briefly mention how you can do the verification efficiently. How to project onto this uniform superposition over everything in the same orbit. That is to use the trick of these permutations you have, because classically imagine you have a random walk. You have a random walk that's mixing. If you apply, for example, you have already a uniform or stable distribution. If you apply a random walk, it will stay in the distribution. And here it's very similar. Since suppose you're starting with a uniform superposition over everything in the same orbit, and you know that if you apply a random walk on the orbit, it's simply one thing walks to the other, right? One element goes to the other, and the whole thing would stay unchanged. So if you apply these random walks to this quantum state in superposition, you would stay as the same quantum state. However, if it's not a uniform superposition, the distribution would change, because there's something. Suppose there is simply element superposition of element 1 and element 2 in the orbit. If you do a random walk, element 2 goes to element 3, and element 1 goes to element 4. Now it's a completely different state. You will be able to find out. So there's a procedure that helps you check after applying a random walk on the state whether the state is changed or not. And if you do that enough times, you will be able to tell whether the original state is a uniform superposition. So I will not go into technical details. I have finished talking about verification. The next question is what kind of security assumptions we need to use to prove the security of this quantum Mani scheme. The first thing is we use is called pathfinding problem. It says that given two random elements in the set, it's hard to find this sequence of permutation that lets you go from one element to the other. So a classical analog is discrete log. Basically, you want to find the exponent that lets you go from one group element to the other. And here in our generalization, these are not necessary group structures. Of course, in fact, you cannot use discrete log because it's quantum insecure. There are more generalized structure of permutations that lets you go from one element in the equivalent class to the other. But there is indeed a post-quantum example of discrete log called group action discrete logarithm. I will not go into. If you are familiar with post-quantum candidates, post-quantum assumptions, this is also one of the famous candidates. Less well-studied than lattices, but still there's a lot of work on it. And this is quite reasonable assumption because there's in fact a lot of mathematical structures where you are given two elements in the same equivalence class, but we are asked to find a path that lets you compute one thing from the other. It will be hard. And the other assumption is what we call knowledge of path assumption. That says if some adversary is able to produce two elements in the same orbit, like out of nowhere, then the adversary in its head, it must have this path of computing one element to the other. So it basically says that there's no way the adversary can sample two elements from the same orbit without using these permutations. If it is able to do so, it must go from, if it produces two elements, it must take the first sample, the first element, and then it makes a sequence of permutations and find the second element. Because all these permutation operations, they are public, but how these equivalence classes, how they are divided, they are not. So it will be very hard for the adversary simply to obliviously sample from the whole set X and try and hope that it gets two elements in the same orbit. So combining these two assumptions, we are able to show that the quantum money we have is secure. I think I'm running out of time, so I'm not going to talk about the instantiations. I've just briefly mentioned that the entire framework was still inspired by a previous work which attribute quantum money from knots. But I'm not a knot theory expert, not even a mathematician, so I cannot really say this work has some analysis, but it's not cryptographic level analysis. There's no correctness proof and no security proof. They simply conjecture that their scheme is secure because it looks secure. But our work basically generalizes what properties you use and abstract these properties to say, okay, if you can do from knots, good, but in fact you can do it from probably many things. So, and if you satisfy the two previous properties I mentioned. And basically, that is everything. So for the two parts of my talk, there are like few open questions. For the first part, of course, is you may still be able to build quantum money from lattices, and there's a lot of ways outside what we have broken. And the second part is, of course, we propose this framework that if you satisfy certain mathematical structures, then you are good. You are probably getting a secure money scheme. But in fact, some of the properties we require are quite strong, and we do not know what kind of standard crypto assumptions, like well-studied, long-standing crypto assumptions, can lead to some of the properties we need. So either breaking our scheme or proving it secure with more well-studied assumptions would be nice. That's it.
Any other time? Maybe we can take one. 30 seconds. Otherwise, let's thank the speaker again.